So we're going to be using these polar coordinates to graph, but then we're going to find the area of the polar region that's generated. And there's a formula that we're going to use, and that is that the area equals the integral from alpha to beta of 1/2 of r squared d theta. So what you need to understand is that if you're looking at a graph, okay, the polar coordinates are really overlaid over what we would consider to be the Cartesian plane. And so what would have been on the unit circle, the radian marks are kind of overlaid on the graph. So we're looking at this one right here that says r equals 4 plus 2 cosine theta. We're asked to find the area inside this oval limacon. All right. So what we're going to do is we're going to integrate this. And if you notice, if you were to overlay the unit circle, notice how it makes a complete revolution. Well, this one is going to go from 0 to 2 pi. So this is where we're going to integrate this from. So what we are indeed trying to find is this area inside the region. And I'm going to shade it very lightly here. All right, but I want you to understand that the whole inside has to get shaded, and that's the area that we're trying to find. And so it's often difficult to find these kind of areas, so the necessity for these polar coordinates and to express them in polar coordinates makes it very useful to be able to figure out these areas, because otherwise it's very hard to do. So what we're going to do here to find the area, like I said, is we're going to integrate from 0 to 2 pi, and we're going to have 1/2 of r squared, and our r in this case is 4 plus 2 cosine of theta squared d theta. And that's what we're going to integrate here. So when we do this, we're going to have the integral then from 0 to 2 pi, and we can continue to write the 1/2 there, but we're going to have 4 plus 2 cosine theta squared. So we're going to do the binomial squared, which is going to give us a 16 plus a 16 cosine theta plus 4 cosine squared theta, and of course all d theta. Now this right here is that binomial squared, and I know in several videos that I've done I've talked about that binomial square. So it's just the FOIL method, if you will, but it's that a plus b squared, which is a squared plus 2ab plus b squared. So I just need you to know that if you're wondering how did you go from here to here. Well, that's what we did. We did the binomial expansion. But if you have to do the FOIL method, you go ahead and do the FOIL method. But now what we're going to do is we can distribute this 1/2 across the board here. And then we're going to rethink the way that this last part looks using trig identities. So what I'm going to do off to the side here is write out a cosine squared identity. So cosine squared theta actually equals 1 plus cosine of 2 theta divided by 2. So we're going to make that substitution in just a minute. All right, but let's go ahead and continue. We distribute the 1/2, and what does that look like? Well, we've got still got the integral from 0 to 2 pi. We've got 8 plus 8 cosine theta. The 1/2 gets multiplied by the 4, so we end up with a 2. And we're going to multiply this by the replacement for the cosine squared, which was 1 plus the cosine of 2 theta over 2. So right here, this should give you an appreciation for everything that you did in pre-calc with those trig identities. This is really why you need to know them, because it makes our life in calculus a lot easier. All right. So what I'm going to do next is I'm going to see that this 2 ends up crossing out with the 1/2. And I'm going to clean this up just a little bit, okay? I'm going to clean it up just a little bit so that I have the integral, and I'm going to create 2 separate integrals just because I'm going to do a u substitution real quick. All right, and then I'll bring it all back together. So we're going to write d theta there, and then plus the second integral here, 0 to 2 pi, and we're going to say, and actually this 1 right here combines with this 8 to give you 9, and I totally missed that. Okay, so that's 9 there. But we're going to take a look at this right here cosine of 2 theta, and that's why I wanted to write it as its own integral, because, so there's my d theta, cosine 2 theta d theta, because I'm going to do a u substitution here off to the side. So I'm going to say u equals 2 theta, so du will be 2 d theta. So I'm going to need a 2 right here in the front, by consequence a 1/2 on the outside, but this helps me account for my du, and this is my u. So this will help me greatly when I'm doing my integration now. So I'm going to get 9 theta plus, and in this case it's going to be 8 sine of theta, plus it's going to be a 1/2. The integral of cosine, of course, is sine, so sine of u, but u is just 2 theta. And we've got that as our integral. Now we're going to evaluate it from 0 to 2 pi. All right, so we integrate that. We evaluate that. Let's move that to the side there. All right, and let's see what else we've got. All right, now what we're ready to plug in. So let's see, we've got a 9 times a 2 pi plus an 8 sine of 2 pi plus 1/2 sine, in this case, of 2 times 2 pi, which is 4 pi. Okay, so all of that minus, we're going to have 9 times 0 plus 8 sine of 0, and then plus a 1/2, and it's going to be sine of 2 times 0, which is just 0 itself again. All right, so let's go ahead and try to see what we can simplify. This right here becomes an 18 pi. The sine of 2 pi here is just 0, so 8 times 0 is 0. The sine of the 4 pi there is 0, so that gets rid of itself, it's 0. This right here is 0. Sine of 0 is also 0, so that's really nice. And again, sine of 0 is 0. So we are left with this right here. Our area of that oval limestone is just 18 pi units. All right, and there's really nothing to it. All right, there's really nothing to it. We've found our answer. Of course, you could probably, if you're using some kind of computer algebra system, probably do this a lot quicker, but you do need to know the process. So you would need to know what to do with that r. Of course, as always, I hope this video was helpful. And remember, like and subscribe.